This is problem 20-17. A 14-inch diameter, 16-pound homogeneous sphere is lowered onto an inclined surface with an initial angular velocity of 3,000 revolutions per minute and 0 linear velocity. If the kinetic coefficient of friction is equal to 0.25 and the angle of the ramp is 20 degrees, determine A, the time t1 at which the sphere will begin to roll without slipping, and B, the velocity v1 of the mass center and the angular velocity omega1 at time t1. Okay, so we are going to be dealing with a sphere, and they give us an initial angular velocity in the clockwise direction, omega naught, and they are assuming that the velocity is going to be up the ramp. And then there is obviously the ramp, which has a 20-degree angle. All right, well, this problem is similar to the problem with the two spinning disks that come into contact with each other, but there is a difference in that there is only one object that is spinning and only one object that will ever move. And so we are still going to have a situation where we're going to have multiple momentum equations, but both of those equations are now going to be on the sphere. Well, why is that? Because in the two disks problem, we had disks that would spin and they would not move. So you had two spinning objects. Now you have one spinning object, but that object is also going to move linearly. So you're going to do a linear momentum calculation and an angular momentum calculation on the same object. Okay, so the mathematical complexity of this problem is practically the same. It's just that the math is going to all be on one singular object. Now, the ramp is obviously still a part of this problem though, and there are going to be two forces at work to manipulate the angular and linear momentum of this ball. So let me put those in as part of the free body diagram. We're going to assume a direction of friction along the bottom of the ball. And then there also is going to be a weight. So we have our weight, but we're going to rotate our axes to being normal and tangential to the ramp. So what does that mean? That means that there will be a component of the weight that is normal to the ramp and a component of the weight that is tangential to the ramp. And it's that tangential component of the weight that matters. Now, keep in mind that since we are talking about a force and location matters, this is a rigid body, that I should put the weight's tangential vector down here at the center of gravity, okay? So just understand that it is this tangential component, but now I'm going to move that component down here. All right, so now let's look at the math, and let me erase these extra components of weight so I don't confuse things. And before I get ahead of myself, let's also put the normal force. Okay, and the weight is 16 pounds. Okay, all right, so let's start first with the fact that this is a rotating object that has inertia, and let's calculate that moment of inertia. So our angular momentum, not the angular moment, moment of inertia is going to be for a sphere, so 2/5, okay, times the mass, which is 16 pounds, divided by the acceleration due to gravity, and then the radius squared. It's a 14-inch diameter sphere, so it's a 7-inch radius, and then converted to feet, and then the whole thing squared. Okay, the answer to that is 0.067, I'll go ahead, 6 slug feet squared. Okay, and then we need to figure out what the frictional force is, because that is a force that is going to be part of the angular momentum calculation. So we will do a sum of forces in the normal, and then that will be equal to the normal force minus the weight, okay, but just the normal component of the weight. So cosine 20 equal to 0 because this sphere is not going to be leaving the ramp. All right, so the normal force, the weight is known, so the normal force is equal to 15.035 pounds. All right, and then we can calculate the frictional force, which is equal to 0.25 times the normal force we just calculated, which is then equal to 3.76 pounds. All right, so now we know our frictional force. We can then come down to our linear and angular momentum calculations. All right, well, first we need the initial linear momentum. It was told that there is a 0 velocity, so there we go, 0. Then we need our impulses. Well, since this is linear, we're going to have an impulse from the frictional force, and we're going to have an impulse from the weight. And so let's first write our frictional force as being the 3.76. But remember, this is impulse, so it's time, some amount of time. That's what we don't know. So we're going to put t. That's what the question is asking us to find, is that time t1. All right, and then minus the 16-pound weight, but only the tangential component, so sine 20 degrees, and then times time t as well. All right, now we can make all of that equal to our final momentum, which our final momentum is going to be the mass times the final velocity, which we also don't know. So we do know the mass, okay, but we are going to find our final velocity. All right, so that's our linear momentum calculation. Let's do our angular momentum calculation. So now we are going to have to be concerned with the angular velocity of the sphere, which we are given as being 3,000 revolutions per minute, which is also equal to 314.2 radians per second. So we're just doing a conversion. All right, and now we can take that moment of inertia, so 0.0676 times the initial angular velocity, so 314.2. And now we can calculate in our impulse. So it's going to be the radius of the sphere times the frictional force. This is going to give us our moment, so 3.76 pounds, and then the amount of time that that moment is being imparted on the sphere, which we don't know. Then we will take our our moment of inertia, and we will multiply times the final angular velocity. So these are finals. Okay, now that leaves us with 3 unknowns: time, final velocity, and the angular final velocity. However, the final velocity and the angular final velocity have a relationship. And so we can do the linear to angular velocity conversion. So the velocity final is going to be equal to the radius of the sphere times the angular velocity final. So there's our third equation. All right, this will allow us to solve for all 3 unknowns. So our time is equal to, and this is T1 that the question is asking for, is 11.85 seconds. Our angular velocity final is equal to 70.1 radians per second. And this is in this is in the counterclockwise direction. And then our final velocity is equal to 40.9 feet per second. And this is in the downward direction. So I forgot to actually ask this in the beginning of the video. What do you believe will be the state of the sphere, both spinning and moving up and down the ramp, at the very moment that the sphere stops sliding along the ramp and starts just rolling? Would it have been going up? Would it have been going down? Would it still be rotating in the clockwise direction, in the counterclockwise direction? And you can see here that apparently this sphere actually started sliding and then started rotating in the other direction and went down the ramp.